Welcome to your data analytics preparation session. Today, we are diving deep into building foundational skills in reading, interpreting, and visualizing data, and by the end of this lesson, you are going to walk away with complete clarity on this topic. So let's get started. At its core, data analytics is the science of analyzing raw data to make meaningful conclusions. It is the engine driving modern business. Why is this so crucial for you to understand? Because every industry, from healthcare to finance, relies on data to uncover hidden patterns, market trends, and customer preferences. By mastering these foundational skills, you are transforming yourself into a highly valuable problem solver. You will learn how to look at a massive wall of numbers and extract a compelling, actionable story. We will start by understanding exactly what data is and how to read it properly, setting the stage for everything else you will do in this field. Let us begin our journey right now. Before we analyze anything, we must establish a clear distinction between two terms people often mix up: data and information. Let us start with data. Data refers to raw, unorganized facts, figures, and symbols. Think of data as raw building blocks. If I give you the number 98.6, that is data. It is meaningless on its own because it lacks context. Is it a test score? Is it a radio station? We simply do not know yet. Now, let us look at information. Information is data that has been processed, organized, and structured to give it meaning and context. If I tell you 98.6 is a patient's body temperature in Fahrenheit, suddenly that raw number becomes valuable information. As a data analyst, your primary job is to take raw, messy data and transform it into clear, actionable information that decision makers can actually use to drive their business forward. To understand how we turn raw facts into insights, we need to look at the data analytics lifecycle. This is your roadmap for any project. The first step is collection. This is where you gather raw data from various sources, like customer surveys, sales databases, or website logs. You cannot analyze what you do not have. Next comes cleaning. This is arguably the most important and time-consuming step. Raw data is often messy, filled with errors, duplicates, or missing values. You must scrub it clean so your analysis is actually accurate. Once the data is clean, we move to analysis. Here, you apply statistical tools and algorithms to find patterns, trends, and correlations. You are asking the data questions and looking for answers. Finally, we reach interpretation. This is where you translate mathematical findings into plain language. You explain what the trends actually mean for the business and recommend the best course of action. Now that we know the process, let us look at the types of data you will collect. Broadly speaking, data falls into two main categories: qualitative and quantitative. Let us look at their fundamental nature. Qualitative data is descriptive and conceptual. It describes qualities or characteristics that cannot be easily measured with numbers. Quantitative data, on the other hand, is numerical. It deals with quantities, measurements, and hard numbers. To make this concrete, let us look at examples. Qualitative data includes things like a customer's review of a product, the color of a car, or interview feedback. Quantitative data would be the price of that car, the exact number of products sold, or a person's height in inches. Finally, how do we analyze them? Qualitative data requires thematic analysis, looking for recurring keywords or sentiments. Quantitative data is analyzed using statistical methods, math, and formulas. Both are incredibly valuable for getting a complete picture. Let us zoom in specifically on quantitative, or numerical, data. In the world of data analytics, we divide quantitative data into two distinct subcategories, and you need to know the difference between them. The umbrella category is quantitative data, representing anything we can count or measure. The first subcategory is discrete data. Discrete data consists of separate, distinct values counted as whole numbers. You cannot have a fraction of these values. For example, the number of employees in a company, or the number of cars in a parking lot. You cannot have half a car or a quarter of an employee. It is a strict, whole count. The second subcategory is continuous data. Continuous data represents measurements that can take on any value within a range, including fractions and decimals. Think of a person's exact height, the temperature outside, or the time it takes to run a race. These can be measured to infinite levels of precision. Let us pause for a quick knowledge check to make sure these concepts are really sticking in your mind. Here is your question: which of the following is an example of continuous quantitative data? Option A, the number of employees in a department. Option B, the temperature in Celsius outside your office. Or option C, the eye color of the participants in a study. Take a brief moment, think about the definitions we just covered, and pick your answer. Is it A, B, or C? The correct answer is option B, the temperature in Celsius. Why? Because temperature can be measured to a highly precise decimal, like 22.5 degrees, making it continuous. Option A is discrete because you can only have whole employees, and option C is qualitative because eye color is a descriptive category, not a number. Understanding these distinctions is absolutely critical before we start reading data sets. Before we dive into the mechanics of reading a dataset, I want you to take a step back and appreciate the sheer scale of the data we are dealing with today. We live in the era of big data. Every single time you click a link, swipe a credit card, or stream a video, you are generating data. Humanity generates quintillions of bytes of data every single day. Imagine massive, sprawling data centers humming with servers, processing millions of transactions per second. This visual represents the incredible flow of digital information powering our modern world. As a data analyst, you are essentially stepping into this massive river of information. Your job is not to be overwhelmed by the volume, but to know how to capture a small bucket of that water, filter it, and find the gold hidden inside. To do that, you need to understand how data is structured, which is exactly what we will cover next. When you finally pull that bucket of data out of the river, it usually comes in the form of a structured dataset. Think of a dataset like a giant spreadsheet. To read it properly, you need to know its anatomy. First, we have rows. In data analytics, a row is often called an observation or a record. Each row represents one single, distinct entity. For example, one row might represent one specific customer, or one specific sales transaction. Next, we have columns. Columns are known as variables or features. These represent the specific attributes being measured for each observation. If the row is a customer, the columns might be their age, their location, and their purchase history. Finally, the intersection of a row and a column is a cell, which contains a single value. This is the actual data point, like the number 35 for a customer's age. Understanding this grid structure is your first step to reading data accurately. Let us look at what a dataset actually looks like in its raw text form. One of the most common formats you will encounter is a CSV, which stands for comma-separated values. It is a simple text file where commas separate the columns. The very first line of a CSV file is usually the header row. This defines our variables. Here we have customer ID, age, and total spend. This tells us exactly what data is stored in each column. The next line is our first observation, or row of data. Customer ID 101 is 28 years old and has spent $250. Notice how the commas perfectly align with the headers above them. The following line is our second observation. Customer 102 is 45 years old and spent $120. When you import this text file into a program like Excel or Python, it automatically converts these commas into a clean, readable table. The CSV file we just looked at is a perfect example of structured data, but not all data is that neat and tidy. We generally classify data into two formats, structured and unstructured. Structured data is highly organized. It fits perfectly into the rows and columns of a relational database or a spreadsheet. Because it is so organized, it is very easy for computers to search, query, and analyze. Examples include financial records, inventory databases, and Excel files. On the other hand, we have unstructured data. This data has no predefined format or organization. It does not fit neatly into a spreadsheet. Think about the text in an email, a collection of photographs, audio recordings, or social media posts. Unstructured data is much more common in the real world, but it requires advanced tools, like natural language processing or artificial intelligence, to extract meaningful insights. As an analyst, you will eventually need to work with both types. We have covered a lot of foundational ground today, so let us lock in these concepts with a quick active recall exercise. I will show you a prompt, and I want you to fill in the blank before I reveal the answer. First prompt: raw, unorganized facts and figures are known as what? Think about the very first definition we discussed. The answer is data. Remember, it only becomes information once it is processed and given context. Next prompt: in a structured dataset, the rows represent individual what? What is the technical term we use for a single row? The answer is observations, or records. Each row is one distinct entity being measured. Final prompt: emails, images, and audio files are examples of what kind of data? Think about how they do not fit into a spreadsheet. The answer is unstructured data. Excellent work. Mastering these terms is your first major step toward becoming a proficient data analyst. Moving right along from our initial data collection, we enter what is arguably the most critical phase of any analytics project, the data cleaning phase. Raw data is rarely perfect. Your first job is identifying missing or null values. If a customer didn't fill out their age, how do you handle that blank space? Do you delete the row, or fill it in? Next, you will spend time removing duplicate records. If a user clicked submit twice, counting them twice will completely skew your final interpretation. Then, we have standardizing data formats. Think about dates: one system uses month day year, another uses day month year. You must force them into a single, uniform standard before you can analyze anything. Finally, you are always on the lookout for handling inconsistent entries, like someone typing New York versus New York. Cleaning data isn't the most glamorous part of the job, but it is the absolute foundation of accurate interpretation. Let's visualize how data actually moves through a professional environment using a standard transformation pipeline. Everything starts on the far left with your raw data. This is the messy, unfiltered information pouring in from your website, sales registers, or user surveys. It is full of errors and completely unready for prime time. That raw information flows directly into the data cleaning stage, which we just discussed. Here, we scrub out duplicates, fix formatting, and handle missing values. Once the data is clean, it moves into data transformation. This is where we might combine two columns into one, calculate new metrics, or aggregate daily sales into monthly totals. We are shaping the data to answer specific business questions. Finally, the refined information reaches the data analysis stage. Only now, after passing through this rigorous pipeline, can we confidently run statistical models, look for trends, and begin extracting the meaningful insights that drive real business decisions. Now that our data is clean and transformed, we need to interpret it. The most fundamental way to interpret a dataset is by finding its central tendency, and the most common measure is the mean, or the average. Let's look at a simple example using the ages of 5 customers. To calculate the mean, your first step is to sum all the values in your dataset. We add 22, 28, 24, 30, and 26 together, giving us a total sum of 130. Next, we need to count the total number of observations, represented by the letter N. Here, we have exactly 5 customer ages, so N equals 5. The formula for the mean requires us to divide the total sum by the number of observations. So, we set up our equation as 130 divided by 5. Doing the math, we find our final mean age is 26. While the mean is useful, it is not the only way to measure the center of your data. Let's compare the 3 primary measures of central tendency. First is the mean, which is the mathematical average. You should only use the mean when your data is relatively symmetrical and free of extreme outliers, because a single massive number can drag the average up. Next is the median, which is the exact middle value when you line all your numbers up in order. The median is your best friend when your data is highly skewed or contains extreme outliers. If a billionaire walks into a room of average earners, the median income barely changes, making it a safer metric. Finally, we have the mode. This is simply the most frequently occurring value in your dataset. You will rely on the mode primarily when dealing with categorical data, like finding the most popular car color. Let's pause for a quick knowledge check to make sure you are grasping these statistical concepts, as this is a very common scenario in real-world data analytics. Here is your question: which measure of central tendency is most appropriate for analyzing housing prices in a city that contains a few multi-million-dollar mansions alongside normal homes? Option A is the mean. Option B is the median. And option C is the mode. Take a moment, think about the impact of those massive mansions on the overall dataset, and pick your answer. The correct answer is option B, the median. Why? Because those few multi-million-dollar mansions act as extreme outliers. If you used the mean, those massive prices would artificially inflate the average, making it look like the typical home is much more expensive than it is. The median cuts through that noise and gives you the true middle ground. We just saw how outliers can ruin an average, so let's formally define what they are and how you should handle them as an analyst. By definition, an outlier is simply a data point that differs significantly from other observations in your dataset. It is the dot on the graph that sits way outside the normal cluster. But where do they come from? Often, they are caused by measurement error. This could be a typographical mistake, like accidentally adding an extra zero to a salary, or a faulty sensor recording an impossible temperature. However, they can also be caused by natural variation. Sometimes, an outlier is a genuine anomaly, like a rare, exceptionally high-value purchase from a VIP client. Because of this, your action plan must always be to investigate first. Never blindly delete an outlier without understanding its context. If it is an error, remove it. If it is real, keep it. Once you have cleaned your data and understood its statistical properties, you reach the most visually impactful part of analytics, data visualization. Staring at thousands of rows in a spreadsheet is exhausting, and quite frankly, the human brain is not wired to process raw numbers efficiently. We are visual creatures. By translating those numbers into charts, graphs, and interactive dashboards, you instantly reveal hidden patterns, trends, and correlations that would otherwise remain buried. A well-designed visualization acts as a bridge between the technical data analyst and the non-technical business stakeholder. It takes complex, abstract mathematical concepts and turns them into a clear, compelling story. Whether you are tracking global sales growth over time or mapping out customer demographics across different regions, visualization is what brings your data to life. It is the ultimate tool for proving your point, securing buy-in from leadership, and driving actionable business strategies based on undeniable evidence. Creating a beautiful visualization is great, but choosing the correct type of chart is absolutely crucial for accurate interpretation. If you pick the wrong chart, you risk misleading your audience. Let's start with bar charts. These are your go-to tool for comparing categorical data, like comparing total sales across 5 different store locations. They make side-by-side comparisons incredibly easy to read. Next, we have line graphs. You should almost always use a line graph when you are tracking trends over time. If you want to show how revenue grew from January to December, a line graph perfectly illustrates that continuous journey. Then, there are scatter plots. These are essential for identifying relationships or correlations between two different numerical variables, like seeing if higher advertising spend correlates with higher sales. Finally, we have pie charts. These should be used sparingly, but they are effective for showing parts of a whole, like market share. Before you can visualize specific trends, you often need to filter your dataset to isolate the exact information you care about. In modern data analytics, SQL is the standard language used to query and filter data directly from a database. Let's look at a basic example of how you might extract high-value purchases. First, you use the select statement to choose the specific columns you want to view. Here, we are asking the database to show us the customer ID and the purchase amount. Next, you use the from statement to specify the source table where this information lives, which in our case is the sales_data table. Finally, we apply our filter using the where clause. By typing where purchase amount is greater than 500, we instruct the database to ignore all the small transactions and only return the rows representing our high-value customers. This targeted filtering is essential for analysis. Let's lock in what we have covered in this section with a quick active recall exercise. I will present a prompt, and I want you to try and supply the missing term before I reveal it. Ready? First prompt, the exact middle value of a sorted dataset is known as the blank. Think about how we handle skewed data. That is the median. It is your best defense against extreme values. Next question, which chart type is best suited for tracking trends over time? Picture the visualization in your head. The answer is a line graph. It perfectly illustrates continuous movement from one time period to the next. Final prompt, a data point that differs significantly from all the other observations is called an blank. What is that anomaly called? That is an outlier. Remember, always investigate your outliers before deciding whether to keep or delete them from your dataset. Transitioning from our deep dive into interpreting data, let's move into the final pillar of our foundational skills, data visualization. You can have the most profound insights in the world, but if you cannot communicate them effectively, they lose their impact. The first core principle of data visualization is clarity over complexity. Your goal is to make the data easy to understand at a glance, not to show off how many fancy chart features you know how to use. Keep it clean. Next, always practice audience-first design. Are you presenting to a technical team who wants to see the raw variance, or to executives who just need the bottom-line trend? Tailor your visuals to the people looking at them. Finally, truthful representation is absolutely critical. It is very easy to mislead people by manipulating axes or cherry-picking timeframes. Always ensure your visual tells the true, unbiased story of the data. How do you actually choose the right chart for your data? It all depends on your underlying goal. Let's break this down into a simple framework. If your goal is to compare different categories, the best choice is almost always a standard bar chart. For example, if you want to compare total sales across different geographic regions, a bar chart makes those differences instantly visible. What if you need to show trends over time? In that case, you want a line graph. This is perfect for tracking something like monthly revenue growth, because the continuous line implies chronological movement. When you need to show the composition of a whole, like market share percentages, a pie chart or donut chart works well, provided you only have a few categories. Finally, to show the distribution of a single variable, like a customer age spread, you should use a histogram to see exactly where the data clusters. Let's look at the anatomy of an effective chart. What actually makes a visualization professional and easy to read? It all starts with a clear, descriptive title. Your title shouldn't just say sales data, it should tell the viewer what the data means, like sales declined in Q3. Give them the takeaway immediately. Next, you must have properly labeled axes. Never leave your audience guessing what the X or Y axis represents, and always include the units of measurement. Then, we have the concept of the data-ink ratio. This means maximizing the ink use to show actual data, and minimizing non-essential ink like heavy grid lines, 3D effects, or distracting background colors. Keep the design minimalist. Finally, use strategic color. Don't just make a chart colorful for the sake of it. Use a neutral base color, and use a bright highlight color only to draw attention to the most important data point. Even experienced analysts sometimes fall into traps when visualizing data. You need to be aware of these common pitfalls so you can avoid them. The most notorious mistake is truncating the y-axis. If your bar chart starts at 50 instead of 0, a tiny difference between two bars will look massive, which is highly misleading. Always start bar charts at 0. Another major issue is using 3D charts. Adding a third dimension to a flat screen distorts proportions, making the data in the front look artificially larger than the data in the back. Stick to 2D designs. You also want to avoid overloading a single chart with too many variables. If you have 5 different lines and multiple axes, your audience will just get confused. Split complex data into multiple simpler charts. Finally, never ignore colorblind accessibility. Avoid using red and green together to indicate bad and good, as many people cannot distinguish between them. Let's look at how you actually generate a chart using code. Python is the industry standard for this, specifically using a library called matplotlib. First, we import the library. We bring in matplotlib.pyplot and give it the standard alias plt to save us some typing later. Next, we define our data. Here, we are creating 2 simple lists, one for our categories, which are the months January, February, and March, and one for our numerical values, representing sales revenue. Now we actually create the visual. By calling plt.bar, we instruct Python to generate a bar chart, passing in our months for the x-axis and sales for the y-axis. Before we finish, we add a clear title and label our y-axis so the audience knows what they are looking at. Finally, we call plt.show to render the completed visualization on the screen. Let's pause for a quick knowledge check to make sure these visualization concepts are sticking. Here is your question: which chart type is best suited for showing the distribution of a single numerical variable? Option A is a pie chart. Option B is a line graph. Option C is a histogram. And option D is a bar chart. Take a moment, think back to our framework, and pick your answer. The correct answer is C, a histogram. Remember, a pie chart shows composition, a line graph shows trends over time, and a bar chart compares distinct categories. But when you want to see how a single set of numbers is distributed, like seeing where most of your customers' ages fall, a histogram is the exact tool you need. It groups the numerical data into bins so you can easily spot the most common ranges and any outliers. Now that you know how to build charts, we need to talk about data storytelling. Data alone rarely changes minds, stories do. The first rule of data storytelling is that context is king. A number means nothing in isolation. If I tell you sales are at $1 million, is that good or bad? You must provide historical benchmarks or industry averages so your audience understands the true scale of the data. Second, you must highlight the why. A good chart shows what happened, but a great data story explains why it happened. Did sales spike because of a new marketing campaign, or because a competitor closed? Connect the data points to real-world events. Finally, every data story should end with a call to action. What do you want your audience to do with this information? Whether it is increasing a budget or changing a strategy, make the next steps incredibly clear. We are nearing the end of our foundational training, so let's lock in what we have learned with a quick active recall exercise. I will give you a prompt, and I want you to fill in the blank before I reveal the answer. First prompt: maximizing the ink used to show actual data is called the blank. What is that term? It is the data-ink ratio. Keep your charts clean and minimalist. Next prompt: to show a trend over time, the best chart is a blank. Think about chronological movement. The answer is a line graph. Final prompt: starting a bar chart above 0 is a misleading mistake called blank. Do you remember the phrase? That is called truncating the y-axis. Always start your bar charts at 0 to ensure you are presenting a truthful, unbiased visual representation of the differences in your data. Let's bring it all together. Over the course of this module, we have built a complete foundation in data analytics. We started by recognizing that data analytics is the process of transforming raw, chaotic numbers into clear, actionable insights. We learned that reading data requires a solid understanding of different data types and structures, knowing the difference between qualitative and quantitative information. From there, we explored interpreting data, which is all about finding the hidden patterns, calculating the central tendencies, and applying real-world context to the numbers. Finally, we mastered visualizing data, ensuring that we can communicate our final story clearly, truthfully, and persuasively to any audience. And that wraps up everything you need to know about foundational data skills for your data analytics journey. In our next class, we will be moving on to advanced predictive modeling techniques, so make sure you stay tuned. Visit Examiverse AI Studio platform to learn more.